We want to talk about oxyacids though, because I got a lot of bio majors and people going on maybe to take biochem and whatnot, and it's going to be super duper duper important. And oxyacid, as the name suggests, is an acid with oxygen, and it's actually an acid where the acidic hydrogen is directly bound to an oxygen. So you got this kind of form: acidic hydrogen bound to an oxygen, and then oxygen is bound to something else. We'll talk about that something else here in a second. Oxyacids are super cool. They tend to be pretty good acids because when the hydrogen gets ripped off, you're putting an extra lone pair on oxygen, and oxygen is very high electronegativity, so it doesn't mind it. As the number, so for example, these are all oxyacids: HOCl, HOCl, oh my gosh, HClO, HClO2, HClO3, and HClO4. They're all oxyacids. And as the number of oxygens on the central atom increases, the acidity of that oxyacid increases. And I'll talk about why here in a second. You can see this with the acid dissociation constant. So this is like an equilibrium constant that, where dissociation is the product side. So you can see when there's only one acidic oxygen, only one oxygen on the oxyacid, it doesn't have a high equilibrium constant. It's 2.9 times 10 to the negative 8. That actually favors not dissociating. Reactant side's favored staying together. But as you increase the number of oxygens, now the product side is slightly favored. When we get to 4, it's actually infinite. Infinity would be the acid dissociation constant. It's so strong. So what about stacking the number of oxygens on the central atom? What about that makes that acid a stronger acid? Well, okay, what happens here is this central atom becomes electron deprived. Because oxygen is such a high electronegativity, 3.5, it's stealing electron density from that central, in this case, chlorine atom. And what that means is that that's going to start to weaken this H to O bond because it wants these electrons to come back in and help stabilize it. So that's why stacking the number of oxygens on the central atom increases the acidity of an oxyacid. Nature has an incredibly important oxyacid. This is what's called a functional group in organic chemistry or biochemistry. And that functional group is called a carboxylic acid. And a carboxylic acid has this general form where you have a carbon double bound to an oxygen that's bound to an oxygen, this is singly bound to another oxygen, and that oxygen is bound to a hydrogen. So here's my oxyacid portion, and this is the bond that gets broken. This is the hydrogen that gets donated, as acids do. They donate hydrogens. Now, what else the carbon's bound to is totally random. It's called an R group. Okay, in organic chemistry, when we don't specify what else it's bound to, we call it an R group. Okay. I want to talk about quickly why carboxylic acids are so darn special and why nature has chosen them to be its acid of choice whenever it needs an acid. So give me a second. Let's do it. So let's draw the generic carboxylic acid. Let's do it this way. And then what else this carbon's bound to is an R group. Now, the simplest carboxylic acid would be if I just put a hydrogen here. If I just put a hydrogen there, this is actually a very special carboxylic acid called formic acid. And this is the acid that insects inject into you when you get a bug bite. Okay, now not like a sting. Like a sting is like there, like, I mean, the initial prick of the sting is formic acid, and then they inject all kinds of other things that people are allergic to. But this would be like if you got an ant bite or bug bite, this is formic acid. In fact, alchemists got this acid by taking in beehives or ant colonies, smashing them up into like a bug slurry. So get a couple hundred ants, smash them up into a couple thousand ants, maybe smash them up into a little slurry, and then they would distill the formic acid off of them. So alchemists actually had this acid hundreds of years ago. But anyways, the simplest carboxylic acid. Acetic acid, the stuff in vinegar, that would be this guy. And of course, if you're a biologist or biochemist, you know that carboxylic acids are important in biology because your DNA contains each amino acid in your DNA linkages contains a carboxylic acid functional group and an amine functional group. And an amine and a carboxylic acid from different amino acids react and form what's called a peptide bond. So that's all that bio crap that I don't care about, right? Okay. But anyway, why has nature chosen carboxylic acids whenever nature needs an acid? Well, the reason is twofold. Number one, when a base comes in and steals this hydrogen, so it acts like an acid, it's a proton donor or a lone pair acceptor, however you want to look at it, and that lone pair goes back on that oxygen. Oxygen actually kind of likes that, right? So oxygen enjoys getting these extra electrons because it's very electronegative and it actually has a negative formal charge. So that's the first reason. The first reason carboxylic acids are so stable is oxygen has a high electronegativity. And it doesn't mind the negative charge. The other reason, I'm just going to put an R group back on here because I'm lazy, so we're going to just call that R. The other reason is this isn't even actually a -1 formal charge. This atom, this structure, this conjugate base is actually stable, which is called a carboxylate. The conjugate base of a carboxylic acid, the carboxylate, is actually stable because it has resonance. So what can happen is we can actually move that negative formal charge up onto the top oxygen. And we have a resonance structure. So it's actually a -1 charge split between two oxygens. It's not even a -1 formal charge, it's a -0.5 formal charge on two oxygens. So the second reason is two oxygens split the -1 formal charge. So that's the second reason that carboxylic acids are super duper stable. So carboxylic acid is a specific type of oxyacid. Not all oxyacids are carboxylic acids, but all carboxylic acids are oxyacids. Amphotheric substances. Amphotheric substances are substances that can act as either an acid or a base. Okay, the most important amphotheric substance is water. Water is a very important amphotheric substance. If you stop and think about it, in order to be an acid, you got to be able, if we look at the Bronsted-Lowry definition, in order to be an acid, you got to be able to donate an H+. And in order to be a base, you got to be able to accept an H+. So water is like the most important amphoteric substance. You can see here in this reaction, water is acting like a base. It is accepting a hydrogen from HCl to become H3O+. It has got room to take on an extra hydrogen. You can see here in this reaction, however, ammonia is stealing a hydrogen to make NH4+. It can act like an acid and donate an H+. So water, depending on what you put in it, the water can accept a hydrogen and act like a base, or the water can donate a hydrogen and act like an acid. Water is not the only amphoteric substances. There are others. So I now want to identify which of these would be amphoteric. And the biphosphate ion, the dihydrogen phosphate ion, not biphosphate, dihydrogen phosphate ion, is amphoteric. It can donate a hydrogen, so it could act like an acid, and it could give away a hydrogen and become HPO4 2-. So it could totally be an acid. And it also has room for another hydrogen. So it could accept an H plus and become H3PO4 neutral. So that is absolutely check amphoteric. HSO4, well, this could get rid of a hydrogen, be an acid, could donate a hydrogen and become sulfate SO4 -2. And it could also accept another H plus and become H2SO4. So that's totally amphoteric. Number 3, okay, this doesn't have a hydrogen. And if you don't have a hydrogen, you can't be an acid, right? Not in the Bronsted-Lowry sense, which is what we use here for this. So that's a no. Carbonate could be a base. This could accept a hydrogen, become HCO3 minus, but it can't donate a hydrogen. It can't be an acid. Number 4 is the opposite problem. Okay, this can donate a hydrogen, but there's no room to put it. And again, this is the harder one to identify. But if you draw the Lewis structure of H2SO4, there's no room to accept an additional hydrogen. That molecule is maxed out. So like that's the highest neutral analog of that substance. So that is also not amphoteric. So, those are amphoteric. These two are not amphoteric. All right. Autoionization of water. The fact that water can act like an acid or a base, that allows it to actually react with itself. Now, this is crazy to think about, but here I got a glass of water. And inside this glass of water right now, there's all kinds of acid-base reactions going on. Water molecules are reacting with other water molecules where one gives away an H plus and the other one accepts it. And this is possible because water is amphoteric. Since one water can act like an acid and the other one can act like a base, then it can react with itself. Now, how much are the water molecules reacting? Well, the answer is, in the grand scheme of things, not very much. We'll talk about the equilibrium constant for this reaction. The equilibrium constant for the autoionization of water is very low. But it does happen, and it actually forms the foundation of our pH scale. So let's take a look at that. Here we go. So the autoionization of water looks like this, and the states of matter are going to be really, really important. Water is a pure liquid. So it's going to be H2O liquid reacts with another H2O liquid. Double-headed equilibrium arrow. In fact, the reaction really favors the left. Very little products get made here. And my first product is the hydronium ion, H3O plus, that gets an AQ, and hydroxide, that gets an AQ. And what I maybe want to do, we'll draw the Lewis structures. So if I draw a water, and I draw another water, what happens in this reaction is one of the water molecules acts like a base. And in the Lewis definition, that's a proton donor. One of the molecules acts like an acid. And in the Lewis definition, that's a lone pair acceptor. We make a new bond here, and then these electrons go onto there. We get H3O plus. And we'll do that guy in red because that's new. And then we get hydroxide, like that. So if we look at this, one of my water molecules acts like a base and steals a hydrogen, so that would be its conjugate acid. And one of my water molecules acts like an acid and donates a hydrogen, that would be its conjugate base, right? If we're labeling conjugate acids and conjugate bases. So hopefully you can see how this reaction is happening. Now, this is made possible because water can be an acid or a base. So if it can be an acid or a base, then one water molecule can steal a hydrogen, the other one can give it away, and you can have an acid-base reaction happening there. Now, how often does this happen? Well, let me give you an idea. If we write the mass action expression for this reaction, because the original reactant water molecules are pure liquids, right? They don't go into my mass action expression. So it's going to be Kc equals products. So my product concentration is my hydronium ion concentration times my hydroxide ion concentration over my reactants are pure liquids, so that's over 1. And since it's over 1, you don't even have to write it. It's just H3O plus times OH minus. Now, at 25 degrees Celsius, so at 25 degrees Celsius, how many water molecules in a liter of water do this? Well, the answer is 1 times 10 to the negative 7th. So 1 times 10 to the negative 7th moles of water react with 1 times 10 to the negative 7th moles of water, we get 1 times 10 to the negative 7th moles per liter of hydronium, and 1 times 10 to the negative 7th moles per liter of hydroxide. So not very much. So at 25 degrees Celsius, the concentration of hydronium is 1 times 10 to the negative 7th molar, and the concentration of hydroxide is 1 times 10 to the negative 7th molar. Right? So now you can calculate the equilibrium constant. So if these are the equilibrium concentrations of hydronium and hydroxide, we can plug those in. So the equilibrium constant for this reaction is 1 times 10 to the negative 7th molar times 1 times 10 to the negative 7th molar. And if you all paid attention in math class, when you have like bases, you can just add the exponents. So negative 7 plus negative 7 is negative 14. So that equilibrium constant would be 1 times 10 to the negative 14. So this is the equilibrium constant for the autoionization of water. So how many water molecules in here are reacting to do this? Well, the answer is not much, right? Look how small that equilibrium constant is. Really favors the reactant side, barely makes any products, right? Barely makes any products. Now, this equilibrium constant is so important. It gets its own name and its own symbol. So let's talk symbol first. This is the equilibrium constant for water. So we call it Kw. It's literally the constant for water, Kw. And the name, it's called the ion product constant. Don't ask me why. I mean, these are two ions, hydronium and hydroxide, and we're multiplying them. So ion product, and it's a constant at 25 degrees Celsius. But I don't know why. I don't know. But anyway, it's the ion product constant. It's the equilibrium constant for the autoionization of water. And this is actually where the pH scale is going to come out. That's where it's going to come from.